Good morning. In this tutorial, I am going to explain how to construct a seismic fragility curve for a RCC building. So on the screen, you are seeing one G+4 structure, which is symmetric in nature. So mass and stiffness distribution along X direction and along Y direction is symmetric. Okay, and therefore the modes, fundamental modes are translation. Just I will show the fundamental modes to you. Okay, so this is the first mode. Okay, so this is first mode is translation mode in X direction, and second mode is along Y direction, which is also a translation mode. And therefore, now see, to construct a fragility curve, we require the analysis data. So the fragility curve, to plot a fragility curve, either we can use the data from the pushover, either we can construct a fragility curve using the data from the pushover analysis curve analysis, or by using a time history analysis, Okay, so therefore, whatever the structure, perform either it put pushover analysis or a time history analysis, and the data from these particular analysis it is required to use for to plot a fragility curve. Now whatever this building, so it is symmetric in nature, and its first mode, fundamental mode along X and Y direction are the translationary mode. There is no torsion. So therefore, we may say this building is the first mode dominated structure. So if the symmetric building is there, in which mass participation in the first mode is more than 85% or 90%, then we can use the pushover analysis data to construct a fragility curve. Now, in this tutorial, we'll discuss how to construct a fragility curve using the data from the pushover analysis. So it is required to perform the pushover analysis. So already the pushover analysis have been performed. Okay, so before to go for the actual calculation of the fragility curve parameters, I will explain what do we mean by a fragility curve. Okay, now seismic fragility curve. Okay, so to understand what is meant by seismic fragility curve, first of all, we must know what are the different damage states. So any structure, whenever it is subjected to some extensive level of earthquake, then there are certain levels of the damages. Okay, so these levels or these damages have been quantified in different handbooks or by various researchers, and they have given the specific name to the damage states. For example, Hazus 2003 one manual is there. So in that, 4 damage states have been defined. Okay, 4 damage states. Which are those? First damage state, it is called as a slight damage state. Okay, it is called as a slight damage state. Second is called as a moderate damage states. So in the case of moderate damage states, so the level of damage is little bit more than the slight damage states. Third damage state is called as extensive damage states. So in that case, the damage level is still severe than the moderate damage states. And fourth damage state is a complete collapse. After extensive damage, fourth one, it is a complete collapse. Okay, so which is in that case, building is completely collapsed. Okay, so this is the fourth damage states. And now in the Hazus, whatever these 4 damage states, its definition have been given. That is what is meant by slight damage, that is which element is collapsed and what is the level of that particular collapse. So definition is given. Not only that, okay, so the description, the damage states have been explained qualitatively as well as quantitatively also, okay, in both ways. So that is in terms of, suppose the spectral displacement is reached up to this level, then it is said to be a slight damage state. If the spectral displacement is more than this, then it is a moderate damage in this way. So it is quantified. Okay, that is another. So just remember, so in the Hazus, there are 4 damage states have been defined. If you consider another researcher, say Wamasco 2002, there is one paper is there, research paper is there. So in that, he has proposed 3 damage states, which are those: immediate occupancy, life safety, and global instability. 3 damage states have been proposed by Wamasco. Then he also quantified this. Okay, so immediate occupancy is said to be occur when the interstory drift reaches to 1%. Okay, then second damage state, that is a life safety damage state. Okay, so he proposed that. So the life safety damage state is said to be occurred when the interstory drift reaches to 2%. Okay, and global instability. So he proposed this particular damage state for the IDA curve, incremental dynamic analysis curve. Okay, so global instability. This damage state is said to be occur when the IDA curve becomes a flatter. Okay, so in this way, so different researchers have quantified these particular damage states. So remember, damage states, whatever the damage states, so each fragility curve is plotted for a single damage state. So here, this particular curve, whatever you are seeing on a screen, this is for a complete damage states. Complete damage states. Suppose in your study 4 damage states you are going to consider. That is immediate occupancy, that is slight damage, moderate damage, extensive damage, and complete damage. Then there will be such 4 curves. This is for slight damage curve. Then for extensive damage curve, the curve will be like this. Then moderate damage state, the curve will be like this. And next is for slight damage state, the curve will be like this. So 4 damage states in your study, then there will be a 4 curve. Okay, so this is about the damage states. That is one thing. Next, now whatever this curve, it is a log normal distribution. Its shape is S shape. Yes, okay, shape is there. Okay, it is a log normal distribution. And to construct a fragility curve, there are 2 parameters, what is known as a seismic fragility curve parameters. Which are those? First is called as a median of the fragility curve. That is the parameter number 1. Median is denoted by lambda. Okay, that is the first one. And second, the standard deviation, which is denoted by beta. Of course, the notations, different researchers have uses the different notations, but mostly this thing, lambda indicate the median value of the fragility curve and beta indicates the variability. Now, what is a median value? Median in the sense center point of the fragility curve. Center point of the fragility curve is called as a median value. Okay, that is the first one. And beta is nothing but variability or standard deviation. Okay, whatever the slope of the fragility curve is, nothing but the variability. More flatter. Okay, more flatter indicate the more variability. Okay, now, so our next task is to estimate these 2 particular parameters. Okay, now perform pushover analysis, and whatever the damage states are there, 4 damage states we will consider. So for the 4 damage states, from the pushover analysis data, we will estimate this particular the parameter, what is called as median value. So median value for slight damage, median value for the moderate damage, median value for the extensive damage, and for the complete damage. So this is from pushover curve. Remember, this is from pushover curve. Okay, and beta value, what is known as the slope of the fragility curve, what is known as the standard deviation or variability. So this value we will take directly from Hazus manual. In the Hazus manual, for different damage states, the beta value is directly given, tables are given. So we will take the value of beta for each damage state directly from the Hazus manual. Okay. Then next is this particular curve, as I said, it is a log normal curve. Y-axis is what? Y-axis is nothing but probability of exceedance of the damage states. Probability of exceedance of the damage states. So it is 20%, 40%, 60%. This is 100% probability. So y-axis is the probability. And remember, what is x-axis? Now, x-axis is nothing but the seismic intensity. Now, seismic intensity is expressed by different parameters. So seismic intensity we can express by using PGA, P ground acceleration. So we on x-axis we can take a PGA, or we can take SAT1, spectral acceleration for the first mode, fundamental mode. SAT1 value for 5% damping is the second one. Also, we can take a peak ground displacement, PGD we can take, or we can take a SD, spectral displacement. we can take a, so different seismic intensity. So seismic intensity can be expressed by different parameters. Okay, so either of this, choose any one which is appropriate for your study. So that particular intensity, that particular parameter should be chosen, should be selected, and that is to be taken on the x-axis. Okay, now there is a selection of seismic parameter. One topic is there, and you will find many research paper on this, that is which particular seismic parameter is appropriate to you. Okay, so in this particular tutorial we will take SD, spectral displacement, as a seismic parameter on a x-axis, and y-axis is the probability. So this is about the fragility curve. Now we will calculate the median value. First of all, we'll estimate the median value from the pushover analysis. Okay, now we will enter into the SAP window. Okay, yes, now this pushover analysis is already performed. I will show you the pushover curve. This is a pushover curve. Okay, pushover curve. Next, now to calculate the median value. Okay, why we require this pushover curve or pushover analysis? To calculate the median value of the fragility curve. Now, the median value of the seismic fragility curve for different damage states. There is one again to define the median from the pushover analysis. Okay, so different researchers again worked on this. Now, one of the researcher is a Barbet. Just I will show the paper of the Barbet. Okay, so this is a figure from the what is called as a Barbet. So this is the paper you will find in 2008, published in 2008. Okay, now this is what is axis? Y-axis is the spectral acceleration. Y-axis is the spectral acceleration, while as x-axis is the spectral displacement. X-axis spectral displacement. Okay, and then this is called as a bilinear curve. From this to this is called as the yielding, and after that the curve is the slope is little bit mild compared to. So this is initial stiffness, and this is the effective stiffness. Okay, so this is called as a Barbet curve. Okay, so this Barbet curve, which is a bilinear in nature, is used to calculate the median values of different damage states. Okay, so here, see, so these are the 4 damage states. First, the slight damage state, then moderate damage states, extensive damage state, and lastly it is a collapse damage states. Okay, or complete damage states. Okay, these are the notation SD1, SD2, D3. Okay, and now slight damage states. So according to the Barbet, slight damage states is said to be occur when the displacement, spectral displacement, will be 70% of the yield displacement. 70% of the yield displacement. Okay, so this is Barbet curve. Okay, so this is the yield displacement. This particular displacement is the yield displacement here, right? Okay, 70% of this, that is, for example, this. So this displacement is called as a yield displacement. 70% of this displacement is this. Okay, then third damage state is the moderate damage state, is this particular point, and this is the complete damage states. This is the complete damage states. Okay, so therefore, this slight damage state, so is said to be occur when the spectral displacement is 70% of the yield displacement. Then moderate damage state is said to be occur when the spectral displacement is equals to dy value, that is spectral displacement. Okay, then extensive damage state is said to be occur when, so the spectral displacement will be equal to dy plus 0.25 du minus dy, where du is the the spectral displacement at ultimate point, right? And the collapse damage state is said to be occur when the spectral displacement becomes to a ultimate displacement, ultimate spectral displacement. So from the Pushover curve, see, from the Pushover curve, we have to estimate, we require the two values first. We require the two values. Which are those? We require two values. First is, what is the spectral displacement at yield point is the first value we require, and what is the spectral displacement at the ultimate point. So these two displacement we will obtain from the Pushover curve. Okay, now we know what is a Pushover curve. Pushover curve, the nature is like this. It is a Pushover curve. Okay, so what is the axis of the Pushover curve? So y-axis is the base shear VB. Y-axis is a base shear VB, while as x-axis is the roof displacement, that is delta, is a Pushover curve. Okay, now, and this is a curved nature. This is curved nature. Now, next step is convert this Pushover curve. Convert this Pushover curve into a, this is called as a capacity curve, right? This is a Pushover curve, or it is also called as a capacity curve. Now, convert this capacity curve into a bilinear capacity spectrum. Convert into a bilinear capacity spectrum curve. So bilinear in the sense it has only one segment is this and second is this. Okay, convert this. So that is VB axis. This VB is to be converted into which axis? SA axis is to be converted into SA, right? And this roof displacement is to be converted into SD. Is to be converted into SD. Okay, so this is the step number one. Okay, so how to convert this? But in the SAP 2000, directly this particular curve is given. This particular curve is, I will just show this particular curve. Okay, now how to convert this? So here also in the SAP 2000, need not necessary to worry about this, how to convert from this to this. Okay, so in SAP 2000, directly this capacity curve, this capacity spectrum curve is given. Just I will show that particular curve. Okay, so this is the second. So first of all, perform the Pushover analysis. Already the Pushover curve we have. Okay, this is the Pushover curve, which is a, as I said, it is a base shear versus roof displacement. Okay, now click here and go for FEMA 356 coefficient method in this. Okay, now see very closely, you just see this. Okay, so I think you might see this red line. Okay, so this is complete, it is a Pushover curve. This is completely Pushover curve, and now it is divided into the bilinear curve. Pushover curve is divided into bilinear curve. Okay, so it is not a capacity spectrum. Capacity spectrum is axis are, this is SA axis and SD axis. Here this Pushover curve is just converted into bilinear curve. So that is from this to this, it is a red line, it is a straight, this is a straight portion, and the curve end here. The curve end here. Okay, now this corresponding displacement. Okay, this corresponding displacement, the curve is like this, from this to this it is straight. Okay, and then it is like this, the curve is like this. This is called as a bilinear curve, and this corresponding displacement is called as a roof displacement at yield point. Roof displacement at yield point, and this displacement is called as a roof displacement at the ultimate point. Okay, now this particular displacement, roof displacement ultimate point, is nothing but this. Here it is directly given, what is known as the target displacement. It is 0.092. So this displacement is known. Okay, now this is a roof displacement at ultimate. Now we'll calculate accurately how much this displacement is. Okay, now how to calculate this? Okay, now to this particular curve, now you just click here, show calculated parameter. Okay, show calculated parameter. Okay, now here some parameters are given. Okay, so in that, see, so this is a stiffness is given. So Ki is nothing but what? Stiffness at initial. So whatever the straight line is there, its stiffness is equals to Ki. So it is given. So this much kilonewton meter. Okay, and the second segment, whatever the second segment is there, its stiffness is, it is a K into E. So how much it is? equal to this much kilonewton meter. So these two stiffnesses are given. Okay, now by using the first stiffness, that is initial stiffness, we can calculate the correctly what is the displacement, roof displacement at the yield point. Okay, so what is the initial stiffness given? It is initial stiffness given 46674.75 is the initial stiffness given. Then we know what is stiffness. Stiffness is equals to, okay, so it is a force, okay, base shear force divided by the displacement. Okay, so this is initial stiffness. So we required, so consider base shear at yield point, what is y, Vy, and this we require displacement at yield point. So the equation for stiffness will be equal to K will be equal to Vy base shear at yield point divided by roof displacement at yield point. So from this, the roof displacement at yield point delta into y will be equal to it is Vy, that is base shear at yield point divided by initial stiffness Ki. Okay, so this is the value. Okay, now Vy is already given. How much it is? That is base shear at ultimate. How much it is? 1364.3453 is the Vy, and divided by Ki is also known, stiffness is also known. So therefore we will get the roof displacement at ultimate. How much answer we are getting? So just we have the calculator. Okay, see. So Vy is 1364.34. Okay, so it is a Vy divided by Ki. Initial segment 4.75 is equals to this much. So how much it is coming? So displacement at yield point is 0.029. So just I will mention somewhere, or we have the word copy. Here we'll just mention it. So it is Vy, displacement at yield point, is equals to how much? 0.029 meter. Okay, similarly, sorry, this is displacement. So it is a displacement, that is roof displacement, actually roof displacement at yield, roof displacement at yield equal to this much. Okay, this is the first value. Similarly, roof displacement at ultimate is equals to how much? Okay, so roof displacement at ultimate is equals to this much, that is target displacement will be this. So it is a 0.092. 0.092 meter. These are the two displacements. Okay. Now next thing is that now this is a roof displacement. Now we will convert this into a spectral displacement. Okay, so now we have this formula. Okay, so this is the equation. So spectral displacement will be equal to the roof displacement in first mode divided by first mode participation factor multiplied by first mode modal displacement at roof. Just I will copy this formula. And just, okay, so this is the formula. So by using this formula, we will convert this roof displacement at yield and roof displacement ultimate into spectral displacement at yield and spectral displacement at ultimate. So first is we required spectral displacement spectral displacement at yield point. This is very required. And second is the spectral displacement at ultimate. Spectral displacement at ultimate point. Okay, so this is called as a du actually. This is called as du and this is called as a dy. Okay, these two values we require for the further calculation. Okay, now first we will calculate this. So what is the formula? Spectral displacement, roof displacement in first mode. Roof displacement in the first mode. So how much it is? Roof displacement is, this is the 0.029 meter. Okay, 0.029 meter. Okay, divided by into bracket. Now first mode participation factor, we require this data. So for that already we have performed the modal analysis. So see the result from the modal analysis. So structure output. So here is the modal information. This is the modal information. Say okay. So this is a modal participation factor. Third, modal participation factor. Okay, convert this. Okay. Now we are doing this calculation in x direction. So in x direction, the first mode is in the x direction. Modal participation factor. Okay, so how much is the value? 18.29. 18.29 is the modal participation factor. 18.29. 18.29. Okay, multiplied by first mode modal displacement at roof. How to get this? Okay, so this is modal participation factor. Now close this. Okay, now the negative sign indicate that positive value. Negative sign indicate that this is opposite in global x direction. Positive means opposite in the direction of global x. So there is no, in the calculation directly only take the value 18.29. Okay, that is one thing. Second, now we'll close this. Now the first mode. Okay, now this is the animation in the first mode. Okay, this is the first mode. Stop the animation. Okay, now at any point you just keep this cursor. And what is the displacement in u1 direction? It is 0.0688. This is called the modal displacement in the first mode along x direction. So it is 0.0688. So it is 0.0688. Okay, so how much is the value? So we'll do the calculation for this. So it is 0.029 divided by 18.29 equal to, and again divided by 0.0688. How much is the value? 0.02322 0.02322 meter is the spectral displacement. Okay, at yield point. Similarly, what is at the ultimate point? Okay, what is ultimate? So what is a displacement at ultimate is 0.092 divided by now this value will be remain same, first mode participant factor and first mode. So this will be remain same. So I will just copy this and just paste here. So it will be remain same. So how much answer will be? Then just will check this. So it is 0.092 divided by 18.29 divided by 0.0688 is 0.073. 0.073. Okay, so meter is the spectral displacement at ultimate point. So this is dy value, this is du value. Okay, now we will enter into Excel sheet now. Enter into Excel sheet. Okay. See, so this is a first value. So spectral displacement at yield point. So how much it is? 0.023, and spectral displacement at ultimate, it is 0.073. Okay, right. Then go for the again. So this is first value 0.023, 0.0. Okay. Then we'll go to the next one. Okay. Then these are the four damage states: slight, moderate, extensive, and collapse. Okay. Now 70% of dy value. 70% dy value is the median value per slight damage. Then dy value is the moderate damage. Then dy plus 0.25 du minus dy is the extensive. So using this particular value, we know dy and we know du. Okay, substitute here, we will get the spectral displacement for each damage states. So I have made the calculation first. So this is called the median value. Okay, first for slight damage, how much it is? 70%. It is 70% of dy value, sorry. 70% of dy value is this value, this much meter. Second is equals to, so what is median value? Equal to dy value. So whatever 0.023 is this value. Third, extensive damage states. So how much it is? It is C3, that is dy plus 0.25 multiplied by du minus dy. And lastly, so this is median value, how much? 0.073. Okay, so in this way, we have to calculate the median value of the fragility curve from the pushover data. Okay, this is the first part is over. Then second parameter is the standard deviation. Standard deviation directly will take from the Hazus manual. Now, where is the Hazus manual? Actually, it is 700-page Hazus manual. So actually, this is the manual. Okay, for your reference, just I will show its first page. So this is the manual, Hazus in the sense hazards in US. So MR4 technical manual it is, and there are number of it is 700 pages actually. So number of such tables are given. So the concern table just I am showing here. So it is table 5.9. Table 5.9. So these are the value of the okay. So it is so we will refer this particular, that is a spectral displacement. So these are given in inches. Remember, these are given in inches. Okay. Now just so this is a first column is a building properties. Okay, so different buildings, type of the buildings are explained in this particular the manual. So W1, W2 is one type of the building. It is a wooden building. Then S1 series. Okay, this is another type of building. Then S2 series, this is another type of building. Then S4, this is another series of this thing. Okay, now RCC building actually starts here. So series is C1. Okay, C2 is another building. Okay, now we will refer this particular C1 series, which is for RCC building. Okay, in the manual you will get the definition of this. What is it? This type of the category. C1L is the low height building. C1M, that is medium height building, and third C1H is a high rise building. Again, so L medium height, low height, medium height, and high in the sense high rise building. That is the third. Okay. Now here, this is the first damage state. It is slight damage states, then moderate damage states, then extensive damage states, and the complete damage state. These are the four damage states. Okay. Now our building is, say it is a medium category. We will call it a medium category, even though it is 4-story building. Just I will demonstrate. I will consider this as a medium. height. So if it is a medium height, then what is the value for beta value? This is for beta, refer beta value, because median value already we have calculated from the pushover runners. So just refer the beta value. So for medium, this is the first value. For slight damage, how much? 0.68. For moderate damage, what is the value? 0.67. For extensive damage, what is the value? 0.68. And for complete damage state, what is the value? 0.81. So these are the 4 beta values from the Hazus manual for the medium class building, medium height building. So in the Excel sheet, these are the 4 values. So these are given in inches, remember. These are given in inches. So first value, these are the Hazus values for beta. It is standard. So first for slight damage, it is 0.68. Then for moderate damage, 0.67, 0.68, and 0.81. These are the values from Hazus 5.9a table. Okay, for medium height building, RCC building. Now these values are standard deviation given in inches. Now it is converted into meter, and these are the conversion. So these values are converted into meter. So this is the first value, beta value, second value, third value, and fourth value. Okay, now we have estimated median value. We have estimated median value in meters for each damage states, 4 damage states, and we have taken the standard deviation value from the Hazus in meter. Okay, this. So for plotting of the fragility curve, these 2 tables are important. Okay, these 2 tables are important. Columns are important. Okay. Now, what is the equation to plot the fragility curve? Okay, now this is the equation given in different researchers have proposed the equation. So this is the equation. So probability, the fragility equation is for probability. So probability of damage state for given spectral displacement. So it is a conditional probability. So how to read this? Probability of damage state for given spectral displacement is equals to phi, in the sense it is a standard normal cumulative distribution function, phi into bracket ln in the sense natural logarithm of SD minus ln of lambda divided by beta. Now we have just, this is lambda in the sense it is median value. So we have just calculated, and this is the beta value directly we have referred from the Hazus state. Suppose to plot a fragility curve for complete damage states. Suppose to plot a fragility curve for complete damage states, then what should be lambda value, and what should be the beta value? So lambda and beta value will be, for complete damage states, the lambda value will be equal to 0.073. Take this value and substitute in that equation. And second, the beta value will in meter will be 0.0203. This is for complete damage states. So these two value just substitute into that particular equation. Okay, for the fragility. Now just I will demonstrate the fragility curve for the complete damage states. So therefore here my heading is fragility curve for the CD, complete damage states. Okay, now make this table like this. So first is SD. Okay, SD value, that is spectral displacement in meter. Okay, now you decide the range of the values. Spectral displacement value. So we can take the range like this. So 0, 0.1, 0.2, 0.3, 0.4, and so on. Or we can take either 0.01, 0.02, 0.03, or we can take 0.01, then 0.12, 0.14, 0.16, 0.18. Decide this thing, whatever this particular the values. Okay, decide the range. Okay, for example, for this building, I have decided the range as the 0.068, 0.069, 0.070, 71, 72, 73, all the values are meter. So as per your whatever the data, okay, decide this particular range. Okay, so it is flexible as per your the range of the values, we can decide this. Okay, then second column is just into this thing. It is you just take the natural logarithm of each value. Okay, so this is there in the Excel also, this particular curve. So second column is the natural logarithm of the ln into SD. Okay, now these values are the ln into SD. Okay, so these are the value is this. Okay, so whatever ln into SD is nothing but second column is ln to SD. Okay, is the second column. Then now the third column. Okay, now third is ln into lambda. ln to lambda. Now we are plotting a fragility curve for CD damage states, right? For CD damage. So what is the lambda value? What is lambda value? Lambda is median value. How much it is? 0.073. So ln of 0.073. ln of 0.073. So it will be same. So ln of, so lambda is same. So therefore all the ln of, so all the values are same. Okay, is the third column. So in the fragility equation where this is ln into lambda, ln into lambda means this term. So this is a column number 3. This is a column number 2. Column number 2, column number 3. Okay. Then next is now in the numerator, in the equation, what is there? ln into SD minus ln into lambda. Okay, so that is, you just ln into SD means this. So this actually, this particular term minus this term is this answer. Okay, similarly here. So this minus this, it will be here. So this minus this, it is a part of just calculation. Okay, is the column number 4. Okay, then divide this value by beta, because in the fragility curve, whole equation, whole term divided by beta. And what is beta in meter for this thing? Beta is how much? 0.0203. 0.0203 is the beta value for this. So therefore, so divide right. So divide the complete numerator, this term divided by beta, we will get this value. Okay, and finally, now whatever this value, it's standard. Just I will show the equation. Okay, so up to now this we have completed. So that is up to this bracket, and then outside the phi is there. What is phi? Phi is the standard normal cumulative distribution function. It is okay. So whatever the answer of this, you just take its normal distribution. So in Excel there is a one command is there. You just click here. So how it is, when we click, how this is obtained, it is this particular, you just equate to, so this normal norms dist, NORMS DIST of this particular column, this particular value will get this value. Okay, similarly norms dist of this value will get this. So like this you will get the all these values. Okay, so these are the probability, and then take a plot of this column on y-axis and SD on x-axis. So this on x-axis. So these values are an x-axis, okay, and these values on y-axis. These on y-axis, and then we will get the fragility curve. This will get the fragility curve, right? So this is the fragility curve for CD damage states. CD damage states. Okay, now to plot the fragility curve for other damage states. So which are those other extensive damage states? Only where the change is, only lambda value will be changed. So use lambda value for corresponding to extensive damage states, and then beta value will change. Only lambda and beta will change. Rest of the calculation will be same. So here to plot a fragility curve for extensive damage states. Extensive damage states, then this will be lambda term and this will be beta term. So you will get the fragility. Use the same Excel sheet. Okay, you will get another curve. Similarly, for moderate damage states, use this value, as a lambda value and this as a beta. So in the same Excel sheet, okay, we can plot this. Or my suggestion is that whatever this particular table, okay, so just copy for the 3 locations. So this is for complete damage states. Second table is for moderate damage state, extensive damage state, and slight damage states. And you just go on changing the lambda value and beta value. Okay, so and then plot here. So on the same plot, you will get the 4 fragility curve. So in this case, the seismic fragility curve from the pushover analysis data we can construct. Okay, so this is the end of the tutorial. Thank you.